Ah, we're good. I should probably make sure people online can hear.
I can hear you.
Okay, so this is where we left off. We have converted the operator equation into an algebraic equation by doing the pre-multiplication by another operator, forming the trace, so on and so forth. Now, here is, for a two-spin, a representation of I minus. And we can associate the non-zero components of the matrix with linking different kets or different bras. So for example, this here would be linking the beta alpha ket to the alpha alpha ket. And that makes sense because you expect I minus to take alpha to beta of the I spin. And this leads into the notion of coherence in NMR. So one refers to, for example, as I plus coherence or IX coherence. And it's one of these things that in NMR, you sometimes forget that or in quantum mechanics, you forget that you don't understand it and you just get used to using it. There's a story that supposedly a student runs up to Feynman and says, "Professor Feynman, tell me the meaning of quantum mechanics." And Feynman says, "Shut up and calculate." So coherence has a bit of a flavor of that. But for example here, sorry about the spacing. These aren't multiplied together. These should be different columns. The formatting got screwed up. Here, for example, is the matrix element for just one spin, single spin. The matrix element between alpha alpha, and for an arbitrary density operator, that's going to end up being the amount of the alpha state squared in an average or ensemble average. And that's perfectly fine. Whereas if you see alpha beta, we end up, because each of these eigenkets is a complex number and has an amplitude and a phase, we end up with the product of the amplitudes. And then this phase difference, because here for the ket, the phase is e to the I phi beta. And for the bra, we have the complex conjugate. So we have e to the I minus the phase. And now when we average, in a simple-minded sense, we can imagine that the amplitudes, the averages of the amplitudes are independent of the averages of the phase. So I've shown that by breaking up the error bars or the average, the over bars into pieces. But the critical thing here then is, what is this average of the phase factors? So that's the average of some delta phi. If I define delta phi as phi beta minus phi alpha, and suppose for a moment the phases were random for the alpha and beta state, what would the average of the exponent be? 0, right? Because e to the I phi is sine phi or cosine phi plus I times sine phi. And if you average cosine over the full range of possibilities, you get 0. You average sine over the full range, you get 0. So there's only this term is non-zero if the phase relationship isn't random over the sample, averaged over the sample. And that's what we mean by a coherence between the alpha and beta states, is that they're averaged over our macroscopic sample. This complex exponential does not average to 0. Now, what part of the density operator would act on beta to turn it into alpha? Because remember, the result of the density operator, any operator acting on a function, is going to generate another function. For our 2x2 state, any arbitrary operator acting on beta is going to generate some mixture of alpha and beta, because those are the only two cats. So if we end up, after sigma acts on beta, we end up with some combination of alpha and beta. Then when that gets integrated with the bra alpha, we can only pick out the alpha part of it. And the operator then, the only operator that turns beta into alpha is I minus, I plus. So this would represents a matrix element in I plus. And for 2x2, that's the only matrix element. The other operator components will just give 0. Because there's nothing else in our 2x2 basis that takes beta to alpha. So we would say colloquially that we have some I plus coherence. What we mean is the phase relationship here between alpha state and beta state doesn't average to 0 over the macroscopic sample. How this happens, you've already seen. So what about the state at equilibrium? At Boltzmann equilibrium, there can't be any preferential phase relationship between the alpha and beta states. If there was, there would be transverse magnetization, and we would then be generating energy from nothing. So that at equilibrium, these terms average to 0, and there aren't any off-diagonal elements. The only terms that survive are the diagonal elements, and they, of course, are the Boltzmann weighted populations of the alpha state and the beta state. And if we generalize to 2 spins or more, the same statement applies. The diagonal elements of the density operator are the populations, and the off-diagonal elements of the density operator represent coherences between states. And we can assign operators that are associated with those particular coherences. And that's kind of shown here. The other thing I should say is I haven't pointed it out yet. This is a good time. That if we take the so-called inner product, alpha, the bra alpha alpha times the ket alpha alpha and integrate, we get 1. We get a number. If we take the bra ket, we have a row vector times the column vector, And when we do the multiplication, we get a number, right? We get the sum of the pairwise things. But if we do things the other order as shown here, where we have the ket bra, the result of that is now a row vector times, or a column vector times a row vector. And the result of that is a matrix. And if we have, say, the simple case of 2 by 2 vectors, we end up with a 2 by 2 matrix. When we have 4-dimensional vectors, we're going to get the 4 by 4 matrix. So the ket bra generates is an operator. The bra ket is a number. Ket bra is an operator. And you can see, for example, here is the alpha alpha ket times the alpha alpha bra. What is that going to do? Well, anything we operate with, if I put a vector on the right-hand side here, the only part of that vector that will survive is the part that's alpha alpha, because all the other parts of that vector, alpha beta, beta alpha, beta beta, are orthogonal to alpha alpha. So this picks out only the alpha alpha part of an arbitrary vector, and we end up with alpha alpha times some number, a fraction of our original vector that was alpha alpha. So this, for 2 spins, is a projection operator that projects out the alpha alpha component. And in my symbols, I'll call that I alpha S alpha. So I've talked about the operators having a matrix representation, but all of the operators also have representations in turn written as these ket bra formulation. And sometimes it's convenient to switch back to that representation of the operators rather than the symbols or the matrices. But here they all are. So for 16, we know we have 16 operators because we have 4 by 4 matrices and there's 16 elements. So here are 4 operators that are associated then with the populations of the 4 eigenstates. This operator represents the population of the alpha alpha state, population of the beta alpha alpha beta beta beta. And then we have a series of single quantum coherences in which one of the operators is raising or lowering operator that changes the quantum number by 1 unit from m minus a half to m plus a half, or m plus a half to m minus a half. So here, for example, this particular operator I identify as I alpha here because both first terms here are alpha, and then S plus because this is going to turn beta into alpha, and that's changing the quantum number by +1. And similarly, I have, I beta S minus, I minus S alpha, all these combinations where one quantum number's magnetic quantum number stays fixed and the other one changes by ±1. And then we have some double quantum coherences where both quantum numbers change. So beta goes to alpha goes to beta, that's I plus S minus. There's I minus S plus, I plus S plus, I minus S minus. And if you count them up, there's 16 operators there. And I could work out what their matrices look like. I'm not going to do it, I don't think. But each of these then, I link to a picture in the energy levels. So here are the 4 energy levels. And I said I alpha S alpha, I associate with population of the alpha alpha state. So those are those 4. And then we have the single quantum operators. And I represent these with these little squiggly arrows that represent a coherence. And for example, I beta S plus will link together the I beta I beta S beta and I beta S alpha, changing the quantum number by 1. And then I beta S minus does the same thing, but going in the other direction. So I can label up all of the 4 states, right? This is the alpha alpha. As I've written this is alpha alpha, alpha beta, beta alpha, beta beta. You can see that from up here. I should have labeled them a little better. But the lower one here I've written is alpha, the alpha alpha state, the alpha beta state, beta alpha, beta beta. So that's just here you can see the 4 levels. And similarly here, I have I minus S beta, the S spin stays beta, and we go from what must be I alpha S beta to I beta S beta. We lowered the alpha state by 1 unit to beta. And then the double quantum terms, here we go the alpha alpha state to the beta beta state, and that's usually called the double quantum transition. And then here we have, and sometimes also called flip flip, because both spins change. And here we have the 0 quantum transitions. One flips, the other flops. So called the flip flop transition. So, yep.
This diagram is for proton, right?
No, because it's for 2 spins. And actually, I've written it as if they were heteronuclei, because for proton-proton, I alpha S beta would have the same energy as I beta S alpha.
No, but for protons, you have alpha energy lower, beta energy higher.
Yes.
So here S plus means it's changing beta to alpha, but energy is lower.
So here I have, for example, this is the alpha alpha state. And S minus here should turn alpha to beta. So this is the alpha beta state. Alpha for positive gamma. Yes. We have minus a half and then times a minus because of this Larmor frequency, right? So the beta beta state is the highest energy, the alpha alpha state. And because I've drawn the alpha beta state as a different energy from beta alpha, I've written this in a general sense that it could be a heteronuclei, but in that case, should be carbon carbon. I mean carbon hydrogen. So the gammas have the same sign. Otherwise, I would just be flipping the signs of alpha and beta. And this will come up important later, actually, when we talk about relaxation, because for a homonuclear system, the 0 quantum transitions are close to an energy of 0, whereas in the heteronuclear case, the 0 quantum transitions can be quite different from an energy of 0. And that has a huge effect on relaxation between heteronuclei and homonuclei. And then, of course, if I don't like the plus and minus representation, right, I can add them together to get representations in the Cartesian frame. And similarly, if I don't like the alphas and betas, I can add and subtract to get representations in the IZ and identity operator frame. But when looking at the energy diagram, this is kind of the simplest way to label the energy diagram. And any coherence then means, for example, coherence between alpha alpha and alpha beta means that there's a non-zero phase relationship between the kets in the alpha alpha state and the kets in the alpha beta state averaged over the sample. And again, if you think back to the picture that I added a few lectures ago, that initial coherence happens because we apply a pulse to rotate Z magnetization into the transverse plane, and our RF field is phase coherent over the sample. So the initial coherence between these levels comes from the phase coherence of the RF pulse. And if the RF pulse wasn't phase coherent over the sample, we would end up with magnetization spread out in the transverse plane, and that those complex exponential factors would average to zero, and we'd have no coherence. We would just end up, if we applied a phase coherent or phase incoherent 90-degree pulse, we would just end up with a density matrix of zero after the pulse, which we would call the saturated state. And if you're online, is there anything you'd like to add to that discussion? And hearing nothing. And then I drew this picture yesterday that I can label the multiplet components then with operators that represent those multiplets. And we get very sloppy in NMR and talk about the operator being the multiplet, but the multiplet intensity is the expectation value of the operator. Right? We have to form the trace with the density operator, etc. So, but it gets, every time I want to mention an operator, saying the expectation value of the operator is just a lot of words. But you should remember, really, it's expectation values that matter. We need numbers. Spectra are numbers. Yep.
I'm guessing those are typos the first time. And as in you meant IS.
Oh, yes. Yes. The top line, yeah. Copy and paste errors. And as I said, we can convert between the different bases. We can go from the I alpha, S alpha to IZ, etc. Just algebraically. Now, we had pictures showing in these operator spaces how we do rotations. And just for completeness, here's a general statement that if we have three operators that obey a commutation relationship, then their evolution is governed by one of these rotation pictures in which we label the axes CAB, and we can do cyclic permutations of the commutator if we need to. If the commutator is zero, then those operators don't evolve relative to each other. They perhaps evolve with respect to other operators. So while we won't need, I'm just going to list everything we need for scalar couplings. If you have operators and you're wondering, do they evolve relative to each other? You just have to figure out what is the Hamiltonian. C would be the operator associated with the Hamiltonian. And then you have to see, do my two operators have a commutator equal to C? So here are things we've already seen. I just written them all down so you can print these out, and tack them up on your wall until you've memorized them. And when I was a postdoc, I just had them all literally pasted on the wall so I could look at them. And here's, for example, for rotations around the z-axis, which we normally think of as chemical shift. It turns out we can't do an RF pulse around the z-axis. We can mimic that by a sandwich of pulses, but the coil that delivers the RF is oriented in the transverse plane. Here's the evolution of scalar coupling. Pulses, etc. One thing that's interesting to think about, let's go, I guess this will do. Let's look at double quantum. Suppose now we have a J coupling between I and S. The energy associated with the J coupling is the product of the two quantum numbers times the J. So take the beta-beta state. What happens to the energy? Right, here's the beta-beta state. What happens to the energy if there's some scalar coupling? Will the energy shift up and down? Let's assume we have a positive J coupling. What'll happen to the energy? Pardon?
Increase.
It'll increase because we have -1/2 times -1/2 times J. So the energy is going to go up by 1/4 of J. What about the alpha-alpha state?
Also,
It also increases by exactly the same amount. So the energy associated with the coherences between alpha and alpha and beta beta is independent of the J coupling. They just move up and down together. So if we take a double quantum coherence, does it evolve under the J coupling? No, because the frequency is associated with that energy difference. So double quantum coherences don't evolve under their mutual J coupling. They can evolve under other J couplings to a third spin, but they don't evolve under their own J coupling. And it's actually a little bit complicated to do kind of the matrix algebra to prove that, but it's quite easy to see looking at the energy diagram. So while in a lot of the course, we emphasize, the operators, etc., sometimes just going back and looking at the energy level diagrams and the coherences can be quite informative.
I'd have to show that IGSC commutes with n minus s minus I plus s plus.
Right.
And you said that's non-trivial?
It's not non-trivial, but it takes some work.
Okay.
Whereas here it didn't take any work. Similarly, what happens to the zero quantum? So here we have alpha beta.
Decrease.
It'll decrease.
Yes.
And here we have beta alpha. It'll decrease by the same amount. So the same thing is true for zero quantum coherence. It doesn't evolve under the J coupling. And this will come up later on. Anyhow, so we have our rules. And once we memorize them, we just have to apply them over and over and over again when we analyze pulse sequences. And then let's come back to detection, a question from the other day. After we do a 90-degree pulse, let's say on IX, we have IX, but if it's a two-spin system, I can think of that as Ix times E, the identity operator for S. And the identity operator is S alpha plus S beta. And Ix is 1/2 of I plus I minus. So I separated those terms all out here. It would be easier to see. I've kept the S alpha factored out, but anyhow. So then during evolution, we know how each of these four things will evolve. We get, for example, I plus S alpha is going to evolve as minus I times omega I plus pi j, assuming certain signs for j, whereas I minus S alpha evolves, have I made a sign error? Minus.
I think it's okay.
Okay. And oh yeah, complex conjugate. So, and then here we have I plus S beta. The J coupling runs in the other direction, and similarly here. So I have four evolving terms in the complex notation. And then I need to take the trace with the detection operator. So let's suppose I'm tuned only to the I spins so that the S spin is a carbon 13, let's say. So my detection operator is I minus. But again, for the two spin system, that's I minus times the identity operator, which is S plus S beta. And now I have to take the trace with the detection operator. And I'm only going to pick out then, the detection operator, it would be I plus S alpha plus S beta. And then when I take the trace, it's going to pick out only the I minus S alpha plus S beta terms. So all of the other terms vanish, and here's my signal. So it's exactly the same as before, except for two spins. I have to remember that F plus would be I plus times S alpha plus S beta. I always have to remember that I have the identity operator there because I need a 4x4 matrix, not a 2x2 matrix. And then I just pick out the two doublet components. And once again, even though the detection operator is I plus, we say we detect I minus because of this trace operation. Yeah?
In this trace calculation, calculation calculating the signal, how do I incorporate receiver phase? How do I incorporate receiver phase?
So in the, basically we would say what we mean by F plus is I plus times E to the I receiver phase.
Okay.
And then as you change the receiver phase, what you pick out will change.
Right.
I think that comes up later somewhere. I think this says kind of exactly the same thing. We have the in-phase doublet. Let's take this operator that you saw would happen. I would get this operator if I put the magnetization on the minus y-axis and then sat on resonance, let the magnetization evolve until the two doublet components were opposed to each other. And at that point, I have the antiphase operator. And I can write out what it is, where now I have this minus sign here because IZ is 1/2 of S alpha minus S beta. So when I convert to the beta alpha, I get this minus sign here. And when I do the same calculation, I evolve during the detection period and then take the trace, I again get two doublet components. But now there's a minus sign. They're out of phase with respect to each other. One multiplet component is up and the other multiplet component is down, just as we did on, on the board the other day. But it's quite important that there be a J coupling. Because suppose the J coupling is 0, that I created this 2-spin operator by evolving a coupling to a 3rd spin. So in fact, there is no coupling between the I spin and the S spin. In that case, J would be 0, and I have no signal. The two components exactly cancel each other. So we talk about an antiphase operator generating an antiphase doublet, but that's only true if there's a J coupling between them, a direct J coupling. And there might not be, again, if I created that coherence by couplings to a 3rd spin, there may not be a direct J coupling. Or during acquisition, I may suppress the J coupling. And I think most people in the class probably know you can turn on something called the decoupler on the spectrometer. And I can, if I'm detecting hydrogens, I can suppress the couplings to carbon-13s. So if I start with an antiphase operator and I turn the decoupling on during acquisition, I'm going to make the J coupling look like it's 0, and my signal will go away because I need a resolved J coupling. Or by resolved J coupling, I mean one larger than the relaxation rates. Because of course, if the lines are only separated by a small amount and the lines are broad, then they're going to tend to self-cancel each other. And one of the reasons why proton-proton experiments are limited in the size molecule you can use is your J couplings are at most of order 12 hertz. And once the line bits get broad enough, because you're working on a big molecule, then all of these antiphase terms start to self-cancel each other and sensitivity goes way down. Actually, there can be some funny effects. And there's a long ago paper called Illusions of Decoupling. Because of course, if we turn the decoupler on, it looks like there's no antiphase operator. But of course, once we turn the decoupler off, the operators will then start to naturally evolve under the J coupling. So there are some experiments that have funny effects if you don't pay attention to that, because the signal you thought went away suddenly reappears. And sometimes it's useful. Let's think about the detection operator another way. So here, our sandwich says we have our starting density operator, say the anaphase operator, and then this expression transforms that during acquisition into a time-dependent free induction decay. And then we form the trace with the detection operator. But it turns out that the trace is independent of cyclic permutations. So while I can't commute matrices, A times B is not the same as B times A in general. The trace of A times B is always equal to the trace of B times A. So cyclic permutations are allowed. So I could move this over to the other side. And then it looks like my operator is independent of time during acquisition, and the receiver is time dependent during acquisition. And that turns out to be really helpful. So if I do that, here I've permuted the trace and now evolved the detection operator. And then here I am at the end of the day. And again, I have a doublet. Well, I did this, it looks like, for the in-phase operator. I have a doublet that depends on the projection of my starting density operator onto the one multiplet operator and the projection of the density operator onto the other. So I'm detecting I minus, like we kind of said our convention is. Here's I minus S alpha, that's one doublet component. Here's I minus S beta. These contractions will pick out whatever my initial density operator was. The part that is proportional to those operators. And here's the expected time dependence, the free induction decay. That free induction decay came from treating the receiver as if it's time dependent. And I get the same answer, of course, that I got before. But here is the useful part, is once I recognize this, I never have to calculate what happens during acquisition, because I know what happens during acquisition. Any operator component that I start with that's proportional to I minus S alpha is going to evolve at the chemical shift of the I spin plus pi j for its coupling to the S spin. And any component of the density operator that is proportional to I minus S beta is going to evolve at the I spin chemical shift, shifted by minus ij, assuming the j's are positive. So from this point on, we don't have to bother calculating what happens during acquisition. We just inspect the form of the density operator at the start of acquisition and just assign what the spectrum is going to look like. So that's a huge simplification. It comes from the cyclic permutation of the trace. And it means actually that detection is the least interesting part of the NMR experiment. The interesting part is what happened to the equilibrium density operator up to the point of acquisition. And at that point, by inspection, we know what the spectrum will look like. And it's the coolest example of that I know of why the cyclic property of the trace is an interesting mathematical property. So questions?
We just have to be like, this is under this particular Hamiltonian, right? So some of the chemical shift Hamiltonian and the Jacob.
Right. And if our detection if we had a different Hamiltonian, we would have to figure out how we rotate the detection operator. But for solution NMR, this is pretty much all it is, all there is. What comes next in here is a little on the boring side that I might let you look at and ask questions next week. Because of course, if you have 3 spins, then you have a much more complicated looking energy diagram. And the question comes up, what are the multiplet structure like? And in organic chemistry, of course, this is really important. In the early days of NMR, there were papers that just tabulated, for all the amino acids, what the multiplet structures were going to look like. But I will let you read through this section and ask questions next time. So we can get on, I don't think, this is really the only important figure you'll see that gives you a recipe. And then one of the problems in the problem sets will let you practice. Now, the sequence tau 180 tau is called the spin echo, and it's probably the most famous effect in NMR spectroscopy, maybe other than 2D NMR. And we'll work it out a little bit. And again, there's more detail that you can look at. So here, for example, I just am going to work this out for a single spin I, and I'll imagine that I started with a 90-degree X pulse, and a 90-degree X pulse, my thumb is on X, my fingers are on Z, I end up with minus IY magnetization. So I'm starting with minus IY magnetization, and now I'll rotate around Z by the chemical shift. So thumb on Z, fingers on minus IY, I rotate towards the plus IX axis. So here, for the time period tau, with a frequency omega I have minus IY cosine omega t. That's the operator I started with, evolving towards plus IX sine omega IT. And we'll use this arrow notation over and over and over. The frequency times time, and the appropriate operator, so the Hamiltonian basically is above the arrow, and starting operator will always be cosine modulated. Destination operator is always sine modulated, and with our rules, we can figure out the signs, the right signs. Then what happens? Actually, I guess I'm doing the, when am I doing this? Let's see a second. Yeah, I lied to you. So I'm doing this for a 2-spin system. And to make things a little simpler algebraically, I'm going to pretend that this first 90-degree pulse was selective on the I spin, so that I don't have any starting ZX or ZY magnetization. But when I come to the 180, I'll decide whether that's selective for the I spin or non-selective. For the homonuclear case, of course, I probably don't have a selective pulse for the I spin. But in the homonuclear cases, if I work things out starting with the I spin with an initial selective pulse in my imagination, and everything else is non-selective, when I'm done, to find out what would have happened if I had a non-selective pulse, I just have to swap all the I's and S's, because it's completely symmetric for a homonuclear spin system. But if I wrote everything down, starting with both I and S, I just get double the amount of algebra, which is hard to fit on the page. So quite commonly, if I'm going to be able at the end of some calculation, fill it out by swapping, I might not do the whole thing. And that's true here. So I'm pretending I have a selective pulse on I to start, but then when I get to the 180, I'll have different results if that's selective or non-selective. So the J-couple, I evolved the chemical shift. And again, in the weak coupling limit, it doesn't matter whether I do shift first or coupling first, because those two terms commute with each other. So I chose to do chemical shift first. And now I have the coupling between the two. So here's the Hamiltonian. Pi JT is the rotation angle. 2 IZSZ is the operator for the Hamiltonian. So IY, doing the minus IY first, minus IY is picks up a cosine term, and it will evolve towards plus 2ixsz by my rules that are in previous things, and that picks up the sine. And the ix has a cosine pi j t, and that rotates towards plus iy, 2iysz with the sine term. And these initial modulations from the chemical shift, those are just numbers, they come along for the ride. So I started with Z magnetization, and at the end of T, it is split into 4 terms from evolution of the scalar coupling and evolution of the J coupling. And of course, an enormous number of more complicated pulse sequences start 90-degree pulse followed by a time delay. So these 4 terms come up over and over and over. And again, if I wanted to know if this pulse was really non-selective, so that I would have minus Iy minus Sy, then I just have to take these 4 terms and swap all the I and S labels. So I would have 8 terms, and this term, for example, would become minus Sy cosine omega S times T, cosine pi JIS times T. So just relabel everything to get 4 more terms. So now, I believe when we look at the next thing, it'll be a non-selective pi over 2 pi rotation. So each operator will be independently rotated by 180 degrees. And the phase is going to be X. So for example, let's just talk our way through. Here we have minus Iy. 180-degree pulse is going to turn that into plus Iy. My thumb is on X, fingers on minus Y, and a rotation by 180 brings me to plus Y. What happens to Ix? Nothing happens to Ix. Ix commutes with Ix. What happens here? Ix commutes with Ix. Sz goes to minus Sz. Thumb on X, fingers on Z, and I rotate by 180 degrees, I end up at minus Sz. Because it was non-selective, so I'm rotating all the operators. And here, Iy goes to minus Iy, Sz goes to minus Sz, and minus times minus is positive. So if I didn't make any change, here we have positive, negative, positive, positive. And now we have the second T period. So each of these operators will rotate under the chemical shift and rotate under the J coupling. So this operator split into 4. So each of these operators are going to split into 4. And I have 16 operators. And it becomes important to do some simplifications along the way. Of course, simplifications along the way kind of assumes you already know what the answer is. And the first time I was working through things like cozies or double quantum filtered cozies, I'd have 5 pages of trigonometry that I would then have to simplify. But after you've done it a while and you learn to simplify along the way, life becomes much easier. But here, for example, then let's just evolve the chemical shift. So after we evolve the chemical shift, we will have 8 terms. And here, for example, I just highlighted in red to show what happens to one of these terms. So this Iy term, picks up another factor of cosine omega it. So I have a cosine squared, and Iy rotates towards minus Ix. So I have a sine omega I. Here's the original two terms, and now here's the new term. The original numerical factors just come along for the ride. A cosine modulation and a sine modulation from the new evolution. And hopefully here, let's just see, we can make a simplification because here we have Iy cosine squared omega I, cosine pi j, and here we have Iy sine squared omega I, cosine pi j, and sine squared plus cosine squared is 1. So be able to collapse those two terms. And then here we have an Ix sine cosine cosine minus Ix. So those are going to cancel. So I can look through here and get some simplification by applying some trig identities. So one thing doing NMR spectroscopy is you're going to make your high school trigonometry teacher very happy because you're going to memorize all of the sine, sum, and difference, angle formulas because you'll use them over and over again. So when I do the simplifications, I come down to two terms. And I still have to do the J coupling, but you can already see what's happened. I've refocused the scalar coupling. At the end of the tau 180 tau, the chemical shift. I've refocused the chemical shift. You'll do this pictorially in the problem set, but the initial magnetization rotated. It then got flipped over by the 180-degree pulse, and then it rotated back to where it came from. And that is the spin echo effect on the chemical shift. We still have to evolve the scalar coupling. So now each of these I have to evolve. Iy under the scalar coupling will evolve towards minus 2Ixsz. Y rotates towards minus x, and because it's the scalar coupling, I pick up the S component. Here, I already have the S component, so minus Ixsz minus Ix rotates towards minus Iy, so I'm going to end up with a minus Iy, and the S will disappear. So I have 4 terms, and I end up then here, Iy evolve towards minus 2Ixsz, whereas minus 2Ixsz rotated towards minus Iy. The antiphase doublet rotated back to an in-phase doublet. The in-phase doublet rotated out to an antiphase doublet. And again, I apply trig identities, and my final answer is that my initial minus Iy term rotated at the end of the spin echo. I had Iy modulated by the cosine of the J coupling for 2t. The J coupling evolved for both the first t and the second t. And Iy should rotate towards, there's 2 minus signs, there should only be 1. Iy rotates towards minus 2Ixsz, and again, I have the sine modulation for the total time period, 2t. So the chemical shift got refocused, and the J coupling evolved as if the pulse wasn't there at all. And that's typical of a non-selective spin echo because both elements of the operators got through. Well, this is really important result, even though it's just one pulse, because we've separated the J coupling from the chemical shift. Just during free precession, during acquisition, the chemical shift and the J couplings evolved together. In the spin echo, we've separated chemical shift evolution from the J coupling. And being able to manipulate independently different parts of the Hamiltonians is the critical thing that makes all modern NMR possible. If we put, you can already see the proliferation of operators. At the end of a pulse sequence, we would have many, many operators at the end of a complicated pulse sequence contributing to the density operator. And the NMR spectrum might be a superposition of many different kinds of NMR spectrum. And a human may not matter to AI, but a human doesn't want to be trying to analyze the superposition of a cozy, a 2-quantum spectrum and a nosy spectrum all piled on top of each other. We want to separate them into different spectra as we analyze. And that depends on the ability to manipulate one part of the Hamiltonian separately from the other. And the spin echo is the first example of doing that. The next part of the notes go through the result for, suppose that the 180 was selective for the I spin and didn't rotate the S spin. And then you can see, I'll leave you to work through the arithmetic yourself to make sure you can do it. Then you find out that you refocus both the chemical shift and the J coupling. And that would be useful, for example, if we just wanted to know what relaxation happened without the interference from shift and J coupling. And I think there's some math we can come back to. So what does this mean is, here's how I wrote a J spin echo. Actually, I said I started with a 90-degree X pulse. There's a little bit of a typo here. But I have a 90-degree pulse to get started, and then T180T. But that ends up looking like I just did a 90, 2T, and then a 180 at the end because of this refocusing effect. And these kinds of simplifications of pulse sequences come up a lot. We'll face with some complicated pulse sequence, we'll want to reduce pieces of it to more simpler blocks when we recognize that we can move pulses around, which you'll see later. And then here is, you can ignore this for the time being. You might ask yourself, and I think maybe the problem set 2 asks, suppose the 180 was selective for the S spin, not the I spin. So in the notes, you have non-selective and selective pulse for the I spin. The other option is selective pulse for the S spin. And I think one of the problems asks you to work that out. So that brings us we have, well, while I reconfigure here, you can ask questions. Any questions online? The online people are very polite, I have to say. Ask very few questions. So we'll just get started then with 2D NMR. And, for the next 15 minutes. And one of the things that to keep in mind as we go, what?
I have a question.
Mm-hmm.
So you talked about simultaneous pi pulses on both INS, as in a non-selective pulse, but when I'm implementing it on a heteronuclear system, I would have to have a pi pulse on proton and a pi pulse on carbon
Yes.
at the same time. Usually these two pulses are not of the same duration
Mm-hmm.
because powers of these channels are
Yes.
how do I sort of make this happen simultaneously?
So in the Brooker pulse programming language, you write them on the same line. But then there are commands to decide whether you want them centered, left aligned, or right aligned.
Okay.
Because take nitrogen 15, a 90-degree pulse might be 30 microseconds, and the proton pulse is 10. And depending on the particular pulse sequence, you may want those to be left centered, left aligned, right aligned, or centered. And Brooker has commands to do those for you, to say how you want it done. It used to be more complicated, but now it's quite simple. But on most probes, say the solution probes, the proton coil and the X coil, carbon or nitrogen, are different coils. And we don't really worry very much then about turning pulses on at the same time. When it comes to turning on a carbon and a nitrogen pulse at the same time, on a solution machine, those are usually the same coil. And it means you're putting a lot of voltage into the coil, which can be bad for the coil, but also heat the sample. So frequently, when you're looking at a diagram of a pulse sequence, say in Journal of Magnetic Resonance, you'll see simultaneous pulses on carbon and nitrogen. But when you look in the pulse program itself, they will only be simultaneous if it's absolutely necessary. Otherwise, they will be offset a little bit from each other. So one pulse ends before the next one starts. And if you work out, we've worked out all 4 spin echoes, where you have selective, non-selective, etc. We can talk about, for example, the case where in the spin echo, where you wanted simultaneous pulses on the same channel, how would you decide to offset the pulse? So when we come back to that in a problem session, you can ask again.
Okay.
But yeah. Particularly as pulse sequence gets more and more complicated. The picture in JMR is a schematic. And one thing that's good is you're now required, to provide as supplementary material the actual pulse sequence. So you can see how it was actually implemented.
So
Mm-hmm.
in the spin echo for non-selective pulses, is it beneficial to use composite 150?
Right. Well, that depends on your spectral width, and of course, and frequently composite pulses are used, adiabatic sweeps, all sorts of things, optimal control. So this is all in the realm of practical NMR as opposed to the theory. And it also depends, quite frequently, one has spin echo trains. And when you have spin echo trains, you have to worry a whole lot about how the imperfections in the pulse accumulate over a chain of spin echoes. And then one gets down to, it can be quite complicated calculations and simulations to try to figure out what's best. And you'll see the subject of spin echoes, the literature is actually absolutely full of papers recommending different things. I'll come back to it, but probably one of the most important kind of theoretical things to say about 2D NMR is because the Hamiltonians are pairwise interactions, a 2D NMR spectrum is a representation of the Hamiltonian. It's really quite remarkable. And 3D, 4D NMR can be useful for resolution, but there's nothing fundamentally new because the Hamiltonians are only pairwise. In contrast, the 1D is a projection of the Hamiltonian down onto the one-dimensional axis. So the natural, as it were, NMR spectrum is a 2D NMR spectrum. And Ray Freeman, who was famous among other things for aphorisms, had the aphorism that a 2D NMR spectrum might not be always the best spectrum to run, but it's the best way to think about NMR because of this pairwise Hamiltonians. And I'll try to remember to point that out as we go. So I'm going to just probably in the next 5 minutes go through this Gedanken experiment that would be called a soft posing. So I imagine, again, that my first pulse is selective. And here I showed the pulse is selective by putting in parentheses which spin it's selective for. And as a visual hint, I made it this short weak pulse. And then I'm going to have a delay and then a non-selective 90-degree pulse, and then I acquire. And I'm going to pretend, for simplicity, that I'm sitting on resonance with the I spin so the pulse can be selective. So the initial density operator is proportional to the I magnetization and the S magnetization. And this is a homonuclear experiment, so I don't need to keep track of polarizations. I didn't write the omega I and omega S here because they're equal to each other. And after a 90-degree pulse on I have minus IY, but I still have SZ because the pulse was selective. And then I have my delay period. For chemical shift, I'm on resonance with the I spin, so nothing happens to the I spin, and S spin doesn't persist, so nothing happens to the S spin. And then I have J coupling, minus IY cosine pi j delta plus 2IX SZ sine pi j delta, same as before. And again, S doesn't evolve under the scalar coupling because SZ commutes with IZ SZ. So that part's easy. You can see why I started with a selective pulse on resonance. Makes my algebra easy. And now I have the 90-degree pulse that's non-selective, and I applied it on the y-axis. So nothing happens to this term. SZ turns to minus. SZ should turn to plus SX. There's a typo. And the important thing is what happens here. So the Y pulse takes X back up to Z, takes X to minus Z. My thumb is on the Y-axis. My finger on the IX axis. I go to minus IZ. On the Y spin, the S spin, my thumb is on Y, fingers on Z now. I rotate to plus IX, plus SX, and so this should be a minus sign, and this should be a plus sign. I'll to fix that, but the signs are less important than what's happened. Here, I have an antiphase operator on the I spin, and after the pulse, I have an antiphase operator on the S spin. And this is called coherence transfer. I transform the coherence for the I spin into coherence for the S spin. I move coherence from one spin to the other. And this then means, this is the critical thing in all multidimensional NMR. We can move coherence from one spin to another, in this case through the J coupling. If the J coupling was 0, this wouldn't happen because sine pi j would be 0. So this can only happen between the I and S spin if the coupling is resolved. But now when I turn on the receiver, what am I going to see? I'm going to have in-phase signals coming from this spin, in-phase signal coming from this spin, and an antiphase signal coming here. This antiphase signal is going to be superposed on the in-phase signal of the S spin, which is a little inconvenient, but it's the antiphase signal tells me I have a J coupling. No antiphase signal, no J coupling. Antiphase signal, I have a J coupling. But they're superposed on top of each other. So here, the IY term, in language we haven't talked about yet, would be called an in-phase dispersive doublet. The second term is in-phase absorptive. Oh, here I fixed things. Here I have the signs right. So XX is an in-phase absorptive doublet at the omega S. And then the third one is an antiphase doublet at omega S. So the signs are right here. The antiphase doublet identifies the fact that there is a J coupling. That's what we're after. However, they're overlapped, which is inconvenient. We can fix that by changing the phase of the first pulse. The first pulse only affects the I spin. It doesn't affect the S spin. And if I go through, everything is the same, except the signs of terms that started on X change, started on I change, and the term that started on S stays the same. And then I subtract the two spectra. And in that case, I null the signal that started on S, and I have only the antiphase signal on the S spin. I still have the signal on the I spin, but I care about the coherence transfer. So now I see it cleanly. And this is an example of phase cycling. I want to add up one signal and suppress a different signal, and I do it by changing the phase of some pulse so that I invert one of the signals and then either add and subtract in order to null the signal I don't want. In more complicated situations, two spectra might not be enough. I might have to add multiple spectra with shifts of phases to isolate the signal I want. But that's just kind of a detail. Here we see right away in the simple calculation that changing the phase of the initial I pulse does what we want. And here's just a picture. So I just did a calculation. Here's the first spectrum. Here's the second spectrum. When I subtract them, I see the pure antiphase signal for the S spin. Here's the magnetization that stayed on in phase on the I spin, didn't get transferred. In our lingo of 2D, this would eventually be a diagonal peak. Magnetization, it was I spin at the start of the experiment and was I spin when I recorded the spectrum. And this will be called a cross peak. Magnetization started on the I spin, but was on the S spin when I came to detection. And again, the appearance of the antiphase signal says there's a J coupling between the two. If the J coupling is 0, these two are going to sit on top of each other and there'd be nothing. I would only see the diagonal. You can also see there's a phase difference between the two signals. Here, this looks like what you think of, a nice absorptive looking line shape. These are so-called dispersive line shapes that we'll have a lot to say about. In this particular experiment, I can't do anything about that. The diagonal magnetization is 90 degrees out of phase with respect to the cross peak magnetization. I can phase the spectrum however I want. I can make these absorptive, but then these become dispersive. And many graduate student lifetimes have been spent trying to fix this problem. We'll see it next time that this is basically a cozy, and next time we'll have the double quantum filtered cozy that fixes this problem at a cost of sensitivity. And then obviously we would like to fix the problem if we could without losing sensitivity. So we did this experiment assuming that we had a fixed delay, and we started with a soft pulse on the I spin. But we'd like to make this non-selective. So we can start with a pulse that excites all the hydrogens and then somehow sort this all out. You can see we have a problem with things sitting on top of each other. And the solution then is the two-dimensional experiment where we start with a non-selective pulse, have a variable time, and then the second pulse. And we start with this time t1 being close to 0. So the pulses are right next to each other. And then we record a spectrum. Then we increase t1, record another spectrum, do it again. So we keep increasing t1, record the spectrum every time, and then figure out what the answer is. So you can look through the next few slides yourself. Here I've drawn the pictures for the different rotations. You can look through the next few to see what the result is going to look like. But this is where we'll take up next time. And once we understand 2D spectra, all the rest of NMR is just turning the crank. Useful, but no new physics. Physics is all in the 2D. So for people who want to stay around and talk about the problems, let's take a couple minute break, and maybe at 2:40, we can talk about problem set, the rest of problem set 1 for a little while. Otherwise, I'll see people next week. And by now, you should be able to do a lot of the problems in problem set 2.
Boy. Yeah. Especially because the same. So I'm just we are taking but 160.
That's why I'm next to it.
Then what is this?
Is it air conditioning?
That is useless.
That is possible.
Uh,
Take some work downstairs. Maybe you lack downstairs, so they can't use.
What's happened during one day? Sure, it has been just one day of different.
You could have won the lottery, you never know.
That's expensive.
Or witness something dramatic.
Oh, that's probably more likely. Especially in the city,
I know, right?
would not be surprised.
You live close to here? Oh, okay. It's an up and down.
Yeah, I just walk.
Huh?
I just walk.
Not here, I mean, like. Lab.
I also walk a lot.
You know,
I'm
what?
like equidistant.
Ah,
I'm like right in the middle.
You guys
Where
need
is
to,
it?
you guys need to remember that all your conversations before that.
Oh no, they're gonna know where I live. They can get the general area of my location now. And that's it.
Huh?
I said that's why I'm here. I'm blocking all of the warmth, so you can't get any of it.
But it doesn't matter, actually, the radiation.
I love the look on your face.
It makes me feel warmer.
I wanted to share. I want to share the camera.
The realization in real time.
Oh, we don't need this anymore.
I think it froze. There we go.
Is it looking at the board? No.
It's looking at you.
Share screen. Second camera. Oh, second camera. But then I don't really need a projector.
On anyone.
Right.
Power.
I can just turn it off.
2 times.
I see. Okay. That. Anyone have any questions or comments about problem 1? Any answers for problem 1A?
H cross omega.
Pardon?
H cross omega. Or H nu. Nu is the Larmor field.
Right. Well, I worked it out numerically, joules. Right, so if you have the Larmor frequency, how do you convert it to energy units?
Multiply with Planck constant.
You have to multiply by Planck's constant, right? H bar omega would give you energy units. I got an energy difference of 3.3 times 10 to the minus 25th joules.
Yes, yes.
A pretty small number. And then in B, one uses that to calculate the populations by Boltzmann's equation. And the ratio that I got, P beta over P alpha, was 0.99992. So very close to 1, equally populated. And in C, the macroscopic magnetic moment depends, of course, how many spins you have. So, yeah, the problem says you have 1 millimolar solute and half a mil. So you can calculate how many spins you have. And then we had an expression for the magnetic moment that's number of spins, gamma squared, h bar squared, b naught over 4 kt. So one has to plug in. And you don't have any sense of that. The magnetic moment has units of joules per Tesla, not, if one works out all the units, you don't have any sense of, what size magnetic moment is big or small. I got 6.7 times 10 to the minus 13th joules per Tesla, but energy is minus mu dot B, and energy you have some sense of. So energy, so if we're in the 500 megahertz magnet, that's 11.7 Tesla. So mu dot B ends up being I got 1.3, 1.2 times 10 to the minus third joules is the potential energy of the NMR sample. And how does that compare to thermal energies?
The orders of magnitude.
On that order, right? KT is 0.6 kcals per mole. And in joules, that's like 2.2 joules per mole. So the magnetic energies are way less than KT. Problem 2 is more or less the same, except you're just comparing different gamma values. And you learn very quickly nitrogen 15 is very insensitive because gamma is so low. 3 we did, right? 90-degree pulse with Y phase. And 10 microseconds is the length of the pulse. And if it's phase Y, the magnetization ends up on X. And then 4 is the first complicated problem. Because now we're off resonance. So the rotation is happening around in the tilted frame rather than in the Cartesian planes.
I think we did that for this. Yeah.
We did it in class with the approximation that the 90 looked like an ideal rotation by alpha preceded and followed by little delays.
Yes.
And that's an approximation if you're close to resonance, which is pretty close to true in this case. But you could do it exactly by doing three consecutive rotations.
I couldn't show that they're equivalent. Or maybe I'm not applying the correct approximation. You want me to read out the 3 components at the end?
So if we did it, now that we have our symbols, life is a little easier than doing it with matrices. Right? So we have in this frame, and I said it was a Y pulse, didn't I?
Yes.
So
Yes, why is hard first?
So our first thing was to then rotate around X. Our effective field is somewhere here. Tilting the theta. So we're going to have to do a rotation around X by minus theta. And then a rotation around Z by alpha. And then a rotation around X by theta to bring us back to the original.
Yes.
And we could do this with the rotation matrices before yesterday. You would have the 3-dimensional rotation matrices that would multiply together. But now, of course, we could say with our symbolic language, we're going to start on IZ and do these 3 rotations. So you certainly can do it with the matrices, and that'll give you great appreciation for the symbols. So we want to rotate around X by theta. And we either rotate around X by minus theta or rotate around minus X by plus theta. They're identical to each other. So if we are on X and we rotate by minus theta, we will go towards the plus IY axis.
Shouldn't it be a rotation like theta and not minus theta?
Well, I want to bring this to the Z axis.
Right, so
Oh, looks like you just plus.
yeah,
Depends on which, if I had applied an X pulse, then it would be a minus rotation.
yeah,
Yeah.
yeah.
Yes. One good thing about paying attention with your hands, you get the sign all right. Okay, in that case, this becomes IZ cosine theta, and then minus IY sine theta. And now we have to rotate around Z by alpha, so nothing happens here. I should be doing this in black. See. IZ. IZ. Cosine theta minus IY sine theta. And then we rotate by alpha around Z. IZ cosine theta minus IY sine theta cosine alpha. And then minus IY will rotate towards plus IX. The sine theta just propagates through sine alpha. And then we have to do minus theta around IX to finish. So IZ cosine theta cosine of minus theta is the same as cosine theta. And the minus theta rotation goes towards plus IY. So plus IY cosine theta sine theta. That takes care of that term. And then we have minus IY sine theta cosine alpha cosine theta. And Y, a minus rotation of Y goes towards minus Z. And the minus signs cancel, or I could have said minus rotation from minus Y goes to plus Z. So plus IZ sine theta cosine alpha sine theta. And then nothing happens to the IX term. Because it commutes. And this then is if we collect terms. We have IZ cosine squared theta plus
Sine squared theta plus alpha.
This should be a theta, shouldn't it?
Yes.
The second thing is the theta. Plus sine squared theta. Cosine alpha. And then we have IY. Sine theta. Cosine theta. 1 minus cosine alpha. And plus sine x sine theta sine alpha. Now, let's suppose one thing to see if we're right is what happens if we were on resonance. If we were on resonance, theta would be pi over 2. And we expect that just to get Ix is the answer. So pi over 2 here would be 0, 1, but the angle would be exactly 90 degrees, which is 0. So this term would be 0. Here we would have, this is supposed to be sine cosine.
Yes.
So this would be 0. And here we would just get 1 times 1, positive Ix. So at least if we go on resonance, we get the right answer. If we were way off resonance, the pulse would have no effect. And we should just have Iz. In that case, theta would be 0. And here we would have 1, 0, 0. So our two limits at least make sense. And then we can ask, for example, if we put the numbers in now, we can calculate how much Z magnetization is left. On resonance, all the magnetization ends up in the transverse plane. Off resonance, some of the magnetization is left on Z. We can calculate how much transverse magnetization we have by doing the vector sum of these two. Okay. Or we could equivalently take 1 minus the square of this and take the square root, because anything that's not on Z is in the transverse plane. So, for example, then the amount of transverse magnetization would be the square root of 1 minus cosine squared theta plus sine squared theta cosine alpha squared, or the sum of the squares of these two things and take the square root. And the phase would be the arctangent of the magnitude of the IY magnetization over the magnitude of the IX magnetization, which is the ratio of these two numbers. And if we plug in and do the calculation, we then get the phase of the magnetization. And when you look at the key, hopefully, I did everything right. The results are, compared to the approximation, are actually quite close. I got for example, I got a phase angle of 7.4 degrees and the transverse magnetization. How much transverse magnetization did I find? Well, the amount of residual Z magnetization was 0.004. So almost everything was in the transverse plane. And when I did the approximate result, I got slightly more transverse magnetization. It overestimated the amount of transverse magnetization a little bit, but critically, the phase error was 7.33 degrees. So less than 1/10 of a degree error in the phase. It looks like maybe in the, oh, actually looks in the notes in the key that I assumed an X phase pulse. But the problem that you have says a Y phase pulse. So I'll have to fix that. Everything is rotated by 90 degrees at the end. So if you're able to then go through that calculation and get numbers that agree, then you know pretty much everything there is about pulses. So it's a really good calculation to do. Problem 5 is the spin echo. So it suggests you do it pictorially. But again, you're going to do it for selective pulse on the eye spin to see how things work out. Problem. Did anyone get to problem number 7?
I think I gave up after the first pulse.
Okay. And again, it's a whole lot easier now that we have symbols than to be trying to do it with matrices. So this was to take care of missetting of the pulse length, or B1 in homogeneity. And in our one thing that can be a little tricky, and I should have indicated it better, is what direction one reads these things. And this was written in the opposite direction from the propagators. The propagators, right, go backwards relative to English. But when people write down composite pulses, they frequently write them in the normal direction. So this says first apply a pulse of rotation angle beta with a 100 and
-1.
minus 120 degree phase, and then apply an X pulse of 2 beta, Whereas if we were thinking in terms of the propagators, you would have thought that 2 beta comes first. And that's just, I don't know, historical mess. So what do we have to do? Is this being applied to Z magnetization? Yes. So now the pulse has a phase that's back Cartesian. So a pulse phase of 100 minus 120 degrees is pointing back here. Right? 120 degrees back this way. And it has a rotation angle around this axis, theta. But I don't really know how to do that. So what we have to do first is rotate around Z by 120 degrees to bring this to the x-axis. And then we know what to do, and then we unrotate. Same as before, it's just here we're getting rid of the phase. So we start with IZ, and we have to do a plus 120 degree rotation around IZ. And what's the answer? IZ again. And then a rotation by beta, now around the x-axis, will give minus IY sine beta plus IZ cosine beta.
Are we assuming on resonance?
Yes.
Okay.
Yeah, because here we just want to know what happens if beta isn't 90.
Right.
There's some RF inhomogeneity. So then we have to undo the first rotation. Rotate back. And IY, so minus IY, sine beta, cosine, whatever 120 degrees is. And we're rotating around Z in the negative sense. So minus IY will rotate towards minus IX. Towards minus IX. I'm rotating in the negative sense. Is that okay?
Yes.
So minus IX, sine beta, sine 120. And nothing happens here. And then the last thing is the rotation IX by 2 beta. So minus IY, sine beta, cosine 2 beta, cosine 120 degrees. IX will rotate minus IY to minus Z. Sine beta, sine 2 beta, cosine 120 degrees. Nothing happens to the IX term. And then the IZ term, you have IZ cosine beta cosine 2 beta. And x takes z to minus y. Cosine beta, sine 2 beta. And then we have to figure out what this result means. Now, one of our hopes in this composite pulse, I mean, if we misset the pulse, so it's not 90, we leave magnetization on the z-axis. So we might hope, do we do a better job of getting magnetization in the transverse plane, i.e., have we minimized the amount of Z magnetization left over? Would be one interesting result. Is that actually what I did? Yes. So how much Z magnetization do we have? Well, IZ cosine beta, cosine 2 beta, cosine beta, cosine 2 beta. Somebody have their phone and can answer what cosine of 120 degrees is?
Minus a half.
Thanks. And we have a minus sign there. So plus 1/2 sine 2 beta. So this is the residual Z magnetization. Now, if we just apply a beta pulse, we would have minus IY sine beta plus IZ cosine beta. So the question is this smaller than that? Which I don't know, but we can make a graph, right, as a function of beta. And of course, if you make a graph as a function of beta, and this is pi over 2, right, for the conventional pulse, this just looks like a cosine wave. Or this is pi over, the ideal pi over 2, there'd be no Z magnetization. And when I made the graph, did I get the same answer? That would be nice if I got the same answer. Looks like I got the same answer. It ends up looking like this. So right around pi over 2, it's flat, which is good, flat around 0. So missetting or B1 inhomogeneity doesn't have an effect on how much Z magnetization is left. But what's the other thing we might worry about? The phase, because the magnetization is now in the transverse plane somewhere. And in the ideal case, right, the magnetization would just all be on minus Y, and all our signals have the same phase. Now, depending on where the transverse magnetization is, we're going to have a phase error. And if this is B1 inhomogeneity in the sample, right, we're going to end up averaging our signal over those phase errors. The phase error, more like this. So it's not flat. I don't actually know if this is a useful pulse or not. I just put it in to make the point, as people start to do composite pulses, they're trying to compensate for some effect, but there's usually not a free lunch. And here, the phase maybe isn't ideal, even though the excitation profile is quite nice. And if we wanted to try to correct the phase, you don't need any more pulses. The composite pulse gets longer and longer, relaxation effects start to become a problem, et cetera. So anyhow. And then I'll leave you to look at the last couple, which are simple pulse sequences. And now that we have our symbols, you should be able to work these out pretty directly. Problems 9 and 10.
I have one question.
Yep.
For what's that? The 180 T90 water suppression.
Mm-hmm.
Here I'm guessing you're trying to wait until the point where water inversion recovery reaches 0, right?
So we're not talking about relaxation effects yet.
Okay.
So that's another way of doing it. Actually, which experiment are we talking about?
9. 180 T90. Okay.
Uh, Why don't I have an answer? Oh, 9 actually. Yeah. Yes, 9
Is inversion recovery.
is inversion recovery, waiting for the water to null.
Water to null, and that's a T1 log 2.
Yeah.
Something like that, right?
Mhm.
So here we are assuming that T1 of water is very different from
Yeah.
protein proton
Mhm.
T1.
Yes.
Uh,
So protein, the T1 is about, a second, let's say.
okay,
And water T1 is 4 seconds.
that's long.
On the other hand, in practice, you have to worry about radiation damping.
Yeah,
We haven't talked about yet.
right. So my question is that,
But 10 then doesn't care. 10
yeah, 10 is
not
just
without
waiting for
relaxation.
difference in offsets.
Yes.
Right.
Mhm.
For 9, I'm wondering, because the supplement to that question is what do you worry about if there is a cryo probe?
Mhm.
And here I'm guessing that if I don't know T1 very precisely, then water very precisely, then error in this waiting duration will lead to some residual signal. Is that the concern?
In the cryoprobe, the problem is that radiation damping is really fast. So if you invert water on a cryoprobe, it'll come back to plus Z by radiation damping in like 10 milliseconds because the Q is so high on the cryoprobe. So then you either want to make use of that, and then you're in the other limit where your spins won't have relaxed at all, but the water will be back on plus Z. Or you have to prevent radiation damping.
What is radiation damping exactly?
Well, we'll talk about it eventually, but the water signal is so large that as it processes, it generates a very large current in the coil.
Oh,
That current in the coil generates a magnetic field that acts back on the water. So you get kind of a feedback loop. So the water that's upside down starts to rotate because of that effect. As it rotates, it generates more current, which generates more magnetic field. So you get this acceleration until you hit the transverse plane, and then it slows down, but will come up to Z. And it depends on the Q of the probe. And so on the cryo probe, it's very fast. So you would either want to make use of that, which kind of inverts this idea. Now the T1 of the protein is long
Right.
compared to radiation damping. Or you have to prevent radiation damping. And you can do that by applying a gradient so that the water is locked on the minus Z axis. And then it just has to use its T1.
Okay.
Or you could detune the probe. There are ideas that aren't very practical, but people have built them, of Q spoiling boxes where you can temporarily change the Q of the probe to stop relaxation damping and then turn the Q back up. But those are the kind of things people write a paper about, but there's no commercial devices to do this. Good, so I'll see you next week. I love all these little problems. Because you start to see building blocks that appear over and over again in more complicated pulse sequences. And the more you can reduce a complicated pulse sequence to a series of building blocks that you recognize, the easier your life is. Thanks everyone online. At this point, it's practice, practice, practice. You have to just get used to doing these rotations in your sleep. Want to go for a seminar?
I am.
Oh, yeah, we have that.
I have a quick meeting here and then we're racing up.
Oh, Martin, do that. Oh, no, I'm teaching.